So thanks to mechanical engineers. Right, so let's go. So where we were up to now is, so we have been able to define what was the best way to do heat recovery inside the system and reduce the minimum, what we named the energy requirement, which was mainly the heat requirement. So what we are going to do now is to look at the possibility of looking at the way we are going to convert the energy that we buy into the energy that we need. And we have seen that we need energy in form of heat. Okay, so the idea would be then to see how we do integrate this part here, which is the energy conversion system, that typically is using the energy that we buy, like the fuel, natural gas, or the electricity, and then distributing this energy in the form of heat to supply the energy needs of the process, so the heat needs of the process. And at the same time, we will have to evacuate the heat here that we have calculated. And this will be done by using also cooling water or air, so that we will be able to release this heat in the environment. So we have seen in the past that based on the definition of the hot and the cold streams, we were able to calculate the heat cascade. The heat cascade that was calculated by applying the problem table methods that allows us to know what is the flow of heat in the system as a function of the temperature. That allows us to know that we need a certain amount of heat to be supplied to the system and a certain amount of heat to be released out of the system. And we have seen that this amount of heat that needs to be supplied was visualized on the one hand on by representing the heat recovery between the hot and the cold streams, and then also by calculating the heat cascade, which is shown here. And so what I would like you to do now, and you will have 5 minutes to do it, is to calculate what is the temperature at which you have to supply the heat, and what is the temperature at which you have to remove the heat out of the system. So up to now we have calculated how much. So we know that we have to supply 20 kilowatt here to close the energy balance. But you know, because you have been studying Exergy in the past, that the value of the energy depends on the temperature level. So what I would like to know now is what is the minimum temperature at which I have to supply the heat? Because a priori this will be the one that has the lowest value per unit of heat. Okay? And at the same time, I would like to know what is the maximum temperature at which I have to evacuate the heat out of the system. So at which temperature can I take the heat, the 65 kilowatt that are here, out of the system? Okay? And let's consider for the moment that you have heat that is available at a given temperature, constant temperature. Okay? So I let you then make the exercise, so you have 10 minutes, discuss among you and try to calculate this temperature. The solutions. But I would like just to summarize what I have heard from your reasoning. So first you have to supply the 20 kilowatt here, and then something that we can say is that a priori the temperature has to be above the pinch. So the minimum of the minimum value is 85. Okay, because the pinch divides the systems into two subsystems. Above the pinch, it's where we have to supply the heat. So it means that the hot utility has to be supplied above the pinch. Another part of the reasoning would be to say that, okay, but we have to heat streams up to 140. So it means that the hot utility has to be at least at 145 or 150 to have a temperature difference. Okay, so it means that we have a maximum and a maximum minimum bound. But then if we read the curve which is set here, that is shown here, what we can say is that indeed we have a stream which is higher than the 140 here, which is this one that has already a given temperature here of 160, right? So it means that this one can be used in order to heat this one, just below. And this is what is revealed in the composite curve that is shown here, where you can see that from this temperature to this temperature we have some heat that is made available by the hot stream. Okay, so this part here from this level to this level is in fact what is happening here, right? And after this, then we have another contribution that is coming here from a second stream that is added here in the list of the hot streams, and then from this point, and this is revealed by this curve here, we have a stream that needs to be heated. And if we make the balance, we realize that we have enough heat here to supply the heat needs up to this point here, just there. Okay, so what we know is that from the temperature which is here to this temperature here, the heat of the hot streams is enough to heat the cold streams. Okay? So, what does it mean? It means that when I'm reaching this point here, and if I want to go to this one, then I will have to supply the 20 kilowatt that is missing. Okay? The same for what is happening below. So below, I know that I need 65 kilowatt of a cold utility, and I would like to know what is the maximum temperature at which I have to cool down those streams. And what I can see is that I have here the same operation. So I have from here to here enough heat to preheat the streams with the heat that is available in the hot streams. Which means that if I have to cool the system, I will reach this temperature here, and this will be the temperature at which I can cool the system. So the consequence of it is that in fact, the composite curve can be divided into the ground composite can be divided into some sections, and the blue sections here and here, in fact, do represent what we name the self-sufficient zone. It's a zone in which the heat of the hot stream is equal to the heat of the cold stream, and this is identified with a vertical by drawing a vertical line here. Okay, so those self-sufficient zones allow me to say that any temperature above the temperature of T2 here is sufficient to supply the heat of the 20 kilowatt that are identified. Okay, and then the way to calculate, so graphically we can identify that the solution is 105 degrees C, but I am in a corrected temperature domain, or the shifted temperature, because I'm looking at the ground composite, which means that I have to translate it into the real temperature, which is by adding delta T, half of the delta T minimum, which means that the minimum temperature at which I have to supply the hot utility is 110 degrees C. And the same reasoning can be done for the cold utility. Okay. Indeed, this analysis comes from the expression on the way we have calculated the heat cascade. In fact, what I can always decide is that I can add with a hot utility at a given temperature heat in a given temperature interval. Okay, so it means that if I'm identifying a given temperature interval, I can add the heat at this interval. And the heat cascade has still to be satisfied. So it means that when I will calculate all the residue in the heat cascade, I will have to be sure that the heat cascaded is positive. Okay? And this explains the reason why I can finally decide to supply the heat here, because here I'm positive, so I'm adding heat. So even if I'm starting here with 0, I'm positive, I'm positive, I'm positive, and just at this point here, I know that I'm not anymore positive. So it means that then I have to add the 20 to satisfy the needs. Okay? So if I want to decide at which temperature I have to supply the heat to a system above the pinch, I have to deduce the self-sufficient zone, and from there I will be able to go down, and until I reach when I reach the curve of the current composite, I will identify the temperature that is needed. And of course, something which is important is that I can then decide perhaps to cut the heat supply into two parts. So for example here, of course, if I have heat available at 450 K, I can supply the whole amount up to this point. If I'm going down and I'm reaching this temperature here, which is 380, I can still supply everything. But if I'm going down to a lower temperature, so for example here 370, then you can see that I will be blocked at this point here, meaning that a part of the heat can be supplied at 370, but the rest has to be supplied at a higher temperature. Okay? And the same if I'm looking at what is happening below. So I can say that I can take this up to this point here with let's say 360 degrees C to take the heat out of this one, but then I will have to decrease the temperature. I will have to go there up to this point. Let's say at 300, this point here at 350. And something which is also important here is that I can read the amount of heat that can be released to the environment, because this is the maximum amount that can be taken out at the ambient conditions, so the 300 degree K that is identified here, and the rest that needs to be taken out of the system by a refrigeration system, okay, below the ambient conditions. And of course, I can read here that I will not buy a refrigeration cycle that is going to take the whole amount that is seen here, but I will just buy one that is going to take this small amount here and let the rest be evacuated by using cold water or cooling system. Okay, so it means that my the heat cascade can be used as a way to identify which are the conditions to be satisfied by the hot utility. Okay? The reality is that the heat that we are going to use is not available at constant temperature. Okay? Most of the reason why most of the people consider it as constant temperature is because they are supplying steam that is going to be condensed. At a given pressure, you start with a vapor state, you go to a liquid state, and you have something which is at constant temperature. Okay? But in reality, this amount of steam needs to be produced by something else. Okay? Like, for example, the combustion of natural gas in a boiler. Right? Now, to be very generic in the definition of the streams, that the hot utility, we have to consider that any utility stream can be considered as a stream, a hot stream, if I'm looking at a hot utility, as a hot stream that will have a temperature enthalpy profile that results, for example, from the combustion, that has an inlet condition, and that will have an outlet condition that is imposed. And so the only difference between the process streams and the utility streams will be the flow that is unknown. Okay? The flow that is unknown and that I will have to calculate. Okay? So what I will have to do now is to calculate the flow of the hot utility, and the way I'm going to do is by looking at the composite curve. I have seen that the self-sufficient zones can be ignored for selecting the hot utility. So what I'm going to do now is to remove the self-sufficient zones and consider that above the pinch, the process is like a cold strip that needs to be heated from this temperature to this one, and then nothing between this temperature and this one, and then again from this temperature to this one. So what we can see there is that the ground composite is defining the process as a big cold stream, so novel cold streams that needs to be heated by cooling down a hot stream. And this hot stream, which will have a temperature enthalpy profile, will have to have a temperature enthalpy profile that is such that it is always above the cold part of the ground composite curve, so the blue line that is here. So any hot utility composite that is above the blue line is a feasible hot utility, okay, because it has the temperature that is high enough to satisfy the needs of all the cold streams that needs to be heated once I will have made the heat recovery. So I remind you that the ground composite is the balance. So it's the is the cold minus the hot that is supplying the recovery. Okay? So the ground composite shows at which temperature I have to supply the heat, and I know that knowing this temperature enthalpy profile, I will be able to then put on top the hot utility profile. And the same will happen for the cold utility. So the cold utility, when I'm subtracting the self-sufficient zone, I will have something which appears like a hot stream that needs to be cooled down. From this temperature to this one, nothing from this one to this one, and then again from there to there. So, and it means that everything that is compatible with this, and in this case I need the refrigeration plus the cold, the cooling water. If the cold streams of the cold utility is below the red curve that is here, then the utility system is compatible. Okay? So it means that now I have a trick to identify at which temperature I have to supply the heat, at which temperature I have to remove the heat, and at which temperature I have to remove the heat below the ambient conditions. Okay? So it means that I have a trick or a tool that allows me to identify which are the best utility that I have to use. Okay? And this is what the ground composite curve is doing. So let's look at which kind of hot and cold utility I can use. Okay? So if you have to supply heat to a process, what is the energy resource that you are going to buy?
Gas.
Huh?
Natural gas.
Natural gas or oil or coal. I would say the natural gas is the best one, but if I have to do combustion. So it means that I have to look at the combustion. So I will not redo the theory. You remember that a fuel is typically a compound or a list of compounds that is composed of atoms of carbon, hydrogen, sometimes a little bit of sulfur, nitrogen and oxygen. That will have to react with air, in fact with the oxygen that is in the air, to produce combustion gases. Combustion gases that will be composed of carbon dioxide that results from the combustion of the carbon, the hydrogen, the water that results from the oxidation of the hydrogen, sometimes some NOx, which is here in the form of NO2, which is the nitrogen that has been oxidized by the oxygen, and sulfur as well, that will be a result of the oxidation of the sulfur atoms. Okay? In order to do this, when we do this oxidation, what is going to happen is that we are going to liberate the energy that is stored in the molecules. Okay? And this will deliver a certain amount of heat, and this heat will be used in order to heat the combustion gases here. Okay? And if the overall amount and combustion gases are composed of what? They are composed of the carbon dioxide, the water, the nitrogen oxide and the sulfur oxide that are here, plus the nitrogen that has entered into the combustion with the oxygen, okay, that will more or less play no role in the chemical reactions, except the fact that it will dilute the heat that is delivered by the chemical reaction, and it will need to be also heated to reach a temperature which is named the adiabatic temperature of combustion. So it's the temperature that is reached if the whole amount of heat that is liberated at the moment of the combustion, so at the moment of the oxidation, is transferred to heat up and used to heat up the combustion gases. And once we have this, then we can calculate the hot streams that is resulting from the combustion. Just for your information, I give you the composition of the air, just to remind you that the air is composed of oxygen and nitrogen, and the nitrogen is part of not the chemical reaction, but of the thermal balance. Okay. I would like also to remind you that there are two definitions for the energy content of a fuel, which are the standard definitions, so the lower heating value and the higher heating value. So the higher heating value is the heat that is obtained by doing a stoichiometric combustion of a fuel in standard conditions, 25 degrees C, predefined, okay? And delivering heat to the combustion gases and cooling down the combustion gases to 25 degrees C with one assumption. So the higher heating value is assuming that at 25 degrees C we will have condensed the overall amount of water that has been produced during the combustion. Okay? Which is indeed impossible because typically the air is not saturated in water, which means that there will be still, even if I'm cooling down the combustion gases to 25 degrees C, there will still be a certain amount of water remaining in the gas phase. So this is the maximum value that we can get, okay? And that's why most of the people consider not the higher heating value, but the lower heating value. And the lower heating value is exactly the same values, except the fact that I'm considering that I'm not going to condense the water that is present in the combustion gases. And the reason why I'm not going to condense the water that is in the combustion gases is because in a boiler, in most of the boilers, I'm not going to cool down the combustion gases to a temperature at which the water, which is diluted with carbon dioxide, with nitrogen and the remaining oxygen, will reach the partial pressure of the saturation of water. So it means that the combustion gases will not condense the water in the boiler itself. And typically this is the reason why, in fact, you will see when we are in a heating mode and we have boilers, you will see white fumes leaving the chimney. It's all the water that is in the combustion gases that when they enter in contact with the surroundings that are really cold, start to condense, okay? But it means that they have not been condensing inside the boiler, okay? So the two different values, the higher heating value and the lower heating value. From there, then we can look at what is the temperature enthalpy profile that we will obtain when we will do a real combustion in a real system. Okay? In a real system, I will not be at 25 degrees C, so I will not be in standard conditions. So it means that I will have, in addition to account for the lower heating value, I will have to account for the contribution of the state of the fuel in the temperature, in the conditions where it enters the system. So it's possible that it will come with a certain amount of energy or without a certain amount of energy. So for example, if I'm receiving the natural gas at 25 degrees C or if I'm receiving it at 0 degrees C, I will have also to heat and to take part of the energy that is supplied at the level of the combustion to preheat the fuel that is entering as well. Okay? The same for the air that is not going to enter just at 25 degrees C, but perhaps at -6. And in this case, I will have also to preheat the air inside the system. But when I will do the combustion, then I will obtain the adiabatic temperature of combustion. What is going to happen then is that I will have I'm in a real device. So it means that the combustion occurs in the burner, in a boiler. And the boiler is not perfectly isolated, which means that there will be some losses due to the high temperature. So adiabatic temperature of combustions are around 2000 degrees C, okay? So it means that even if I'm really well isolated, there will be some radiations and you will feel that the boiler is hot. And if you feel that the boiler is hot, it means that it is losing heat, right? And it is losing mainly by radiation, okay? And typically we say that there is an order of magnitude of 2% of the lower heating value of the gas that will be lost at very high temperature just because the boiler is not perfect. But after this, the remaining amount of heat will be available for heat exchange from this temperature, minus the 2%, up to the 25 degrees C, and this makes the lower heating value. Okay? It makes the lower heating value. Now, something that is important is that, of course, I could represent as a function of the temperature something like this, which is not in reality a straight line. Okay, it's a little bit curved because the Cp is not really a constant over 2000 degrees C temperature scale. Okay, but I will represent it as a constant, but I will have also to recognize that when I'm doing the pinch integration, the pinch representations, I'm mainly trying to represent the convective countercurrent exchange, which means that I will not most probably access this very high temperature operation here. Okay, and so typically what we do is that we cut the curve into two zones. Above 850 degrees C, we can consider that we are mainly looking at radiative heat exchange and that there will be no pinch created in this scale. So the radiative is more, is a T4 exchange, okay? And therefore it's not well suited to be represented with a composite curve. What is happening below 850 degrees C, where mainly the heat transfer phenomena that is then the majority one is the convection, is going to represent what is happening from this point to the 25 degrees C. And I know that I will end up this heat exchange not at 25 degrees C, but at the stack temperature, which is typically 120 degrees C also. Which means that this part is the heat that is available for the boiler that can be supplied to the process. Okay? Which defines then from this point to this one, the temperature enthalpy profile that I will have to take into account in order to make the calculation of the flow of the fuel in the boiler. Okay? And I will have also to recognize that from this temperature to this one, this is an amount of heat that I have obtained from the fuel that I have bought. Okay? So this is something that I have paid for, right? But that I'm accepting to release in the environment. Okay? So at the end, I will have, in fact, two losses. The one that are here, that are radiated to the environment, and another one that is here, which is from this point to this one, which is then lost at the stack. Okay? Leave the system as hot gases. Okay? I was also explaining that there is a presence of water, and the presence of water is going to create some opportunity, because if I can condense water, water has a high condensation heat load, around 2,400 kilojoule per kilogram of water condensed, so it would be nice to try to recover this one. But what we have to recognize is that we will access this amount of water only if the partial pressure of water is high enough to condense water. So it means that the temperature is low enough. Okay, and the fact that the water is not 100% in the combustion gases, because it is coming with oxygen and with nitrogen and carbon dioxide, it has a partial pressure which is below the atmospheric pressure. Okay, which means that it is going to start condensing at lower temperature. So if I if I have something which is not diluted, so very perfect combustion without air excess, then I will start condensing at 60 degrees C. If I'm a little bit more diluted, then you can see that the temperature is going to decrease. And each time I'm going to, if I reach this temperature there, then I will be able to exploit a little bit more than the lower heating value by condensing water. But it means that the tubes have to be at 60 degrees C. So it means that the pinch has to be below 60 degrees C so that I can recover this amount of heat. Okay? Right. And this is just the conclusion of this. Now, I have two temperatures. On the one hand, the temperature of the adiabatic combustion. On the other hand, the stack temperature. And I have to define what is the amount of flow that I have to put in the system. And if I'm changing the flow, the two temperatures will not change, but the slope will change. And the cost will change as well. Okay? So, what is the best case? This one is not the best because I have a flow which is too big, and I have a big heat loss here and a heat excess here. But this one is not correct neither because the temperature profile is not satisfied. Okay? So it means that at the end, I have to calculate the flow in such a way that the curve of the combustion is just above the curve of the process. Okay? And what you can see here is that it has activated, so the flow is going to activate a pinch point in this case. Okay? And what is also going to happen is that I will have an excess of heat available. That is the amount that I have bought together with the fuel that I have bought. Okay? So it means that it is coming with the price. But unfortunately, the temperature is not, the temperature of the heat requirement in the process is such that I have to accept to increase the flow and spend more than the flow that I would have calculated to just produce the amount of heat that was needed. Okay? So, it means that I have to calculate the operating cost, consider the cost of the fuel, multiply by the flow, and the flow is going to define the slope of the curve between the two temperatures that are predefined and correspond, and that are a characteristic of the fuel that I'm going to use. And the pinch, in this case, is going to create the minimum flow. And if it is not the same as the one of the process, it is typically named a pinch, a utility pinch. Okay, that defines the minimum cost with this utility that is used. So here we have seen that if I have a hot utility resulting from the combustion, I will have two temperatures that are fixed and comes from the utility, and that I will have to find the appropriate flow rate in such a way that I will satisfy the needs of the system. And the minimum flow rate is defined by how good the hot composite coming from the hot utility is matching the cold composite coming from the process. So there is, however, another degree of freedom that comes from the fact that I can choose different fuels, for example. Okay, so I can have waste solvent, I can have coal, I can have wood, I can have natural gas. Each one will come with another cost, okay, and also adiabatic temperatures and stack temperatures. Okay, so it means that at the end I will have to make, for the same amount of energy that is useful for the process, I will have to make an evaluation and choose which one is the best. And it will depend not only on the flow, and you can see, for example, that this one has a lower temperature here and a higher temperature here, but it will result into another flow because it is going to satisfy the needs of the process in this way. While the red one will have a higher temperature here, a lower stack temperature here, will have a heat excess here, and the flow will be calculated by the activation of the pinch point here. Okay, so it means that I will have to make an analysis of which one of the two is the best. Okay? If I have 2 fuels, I will do it for 2. If I have 10 fuels, I will have to do it for 10 fuels. Okay? Another dimension to it is that you remember that I said that it was important to look at the temperature level of the hot utility. And one of the reasons why I'm saying this is because I know that the lower the temperature, the lower is the value of the Exergy. But of course, if I have a certain amount of heat available from a resource, I have to ask myself, how can I reduce the value of the heat that is supplied at a lower temperature and compare it with a higher temperature? So if I'm asking you, so what would be the mechanism that would allow you to have a temperature at 100 degrees C, which has a lower value, so a lower cost, than a temperature that is at 200 degrees C? So how would you explain that there is a difference?
The mass flow you would need would be different.
Say it again?
The mass flow of the fuel you would need would be different.
No, it would be the same amount of heat, but at 2 different temperatures. Okay? And I'm saying that the cost of the heat will be different because it is at higher, it will be higher if it is at higher temperature than if it is at 100 degrees C. So how could you explain this? So the Exergy explaining this, we know that if the temperature is lower, the Exergy value is lower. Okay, so what does it mean? Exergy is
Useful energy.
huh?
Useful energy that can be turned into.
Yeah, under which form?
It's working.
In form of work. Okay? So what does it mean? It means that if I'm supplying heat at 100 degrees C, and if I have something which is at 200 degrees C, between 200 and 100, I will have the possibility of producing work. Okay? Which is the principle of cogeneration. So it means that when I will look at supplying heat to a process, I will try to see if I cannot convert the fuel that I'm buying into work first and then afterwards deliver the heat. Okay? Which is the principle of the cogeneration. And typically a cogeneration engine will have, based on the flow of lower heating value of fuel that is entering there, we will produce a certain amount of electricity and a certain amount of useful heat. And the balance, which is the balance between the amount of energy that is entering here and the useful energy forms that are here, will be the losses that will be released in the environment. If I have an engine, it will be in the combustion gases. Okay? So it means that I'm going to try to see if I can then buy fuel and supply heat together with the co-production of electricity. So this is the principle of the cogeneration. So how does it work when I'm doing process integration? So there is one example is a gas turbine. So what is going to happen with a gas turbine is that I'm going to burn gas at 50 bar here in compressed air. And the compressed gases that will be hot here will be then expanded in a turbine, and there will be a net production of electricity. The typical efficiency of these systems with today's technologies are between 30 and 38% based on the lower heating value of the fuel. It means that when I have produced electricity here, I will have hot gases that can be cooled down, and if they are cooled down to 25 degrees C, they will deliver the whole amount of heat available. Unfortunately, I will have to stop at the stack temperature, which is not the 25 degrees C, and typically what we can say is that 85% of the energy can be recovered, from which I have to deduce the 30 or the 38 that I have produced in form of electricity, which means that I will have between 55 and 47% of heat available. And I will have to take care from the fact that the amount of heat that is available here, so the temperature enthalpy profile that I have here, has to be above the line of the composite of the process, which allows me then afterwards to supply the to calculate what is the flow of hot gases that I am expecting out of the gas turbine. And knowing the amount of the flow that I'm expecting out of the gas turbine in form of heat, I will have the flow, and if I have the flow, then I will be able to calculate the amount of electricity that will be produced by the gas turbine. Of course, this analysis is perhaps not so easy than the one that I have set now, because if you calculate the flow of natural gas that you need, you will end up with a gas turbine of 7.33221100 megawatts, okay? And then you will look on the market and you will find there is an 8 megawatt and a 10 megawatt available on the market, okay? And then you will have to choose which one you use, okay? If you take, let's say that there is a 6 and a 6 and a 10. If you take a one that is too big, then you will have to operate in part load, so you will put less fuel in the combustion here. And if you take a one that is too small, then what you will do is that you will add some gas here to do post-combustion. So it means that you use the hot air that is still leaving the gas turbine, and you will add some gas in order to complete the heat load that is needed. Okay, so the idea here is that you will have to adapt, but it means also that you will have options. Okay, so keep in mind that most probably you will have more than one option to decide which one is the best solution. Okay, and don't forget that everything will be related to the flow that is defined by the pinch. Okay. This will be the same for the other type of cogeneration units that are well known today, which is the internal combustion engine. Okay? An internal combustion engine is more or less like 4 steps gas turbine, so it's more or less the same. In a piston you compress air, then you inject fuel, you burn, and then you expand the hot gases, and you do it again and again and again. Okay? It's just that you have pistons instead of having rotating machine or turbo machinery. The cogeneration engines have, in fact, present two heat sources. On the one hand, the combustion gases. Okay, at the exhaust of the engine, you have hot gases that needs to be cooled down. Okay, and this will create this hot stream here. And on the other hand, you know that you have an internal combustion engine in your car, and a typical problem of the internal combustion engine in the car is that you have to be sure that you have a radiator that is there to cool down the engine, otherwise the engine is going to break. Okay, so the idea is, and the way we cool the engine is by circulating hot water, and typically you have an indicator of temperature in your car around 90 degrees C. If it goes above, then you know that you have a problem and it's time to stop, right? So the 90 degrees C is an order of magnitude at which you can recover the heat from the cooling of the engine. So this is typically what we are going to use as a hot stream from 90 to 80 degrees C. It can be higher, okay? With a risk is that the cooling water starts to boil. Okay, so you pressurize therefore the water, and then you will have another risk is that you have mechanical stress inside the engine, because if you pressurize the cooling water, it means that there will be some parts, and it's mainly the places where you have leakage, so you protect from the leakage in the engine. which will see different pressures. So inside the engine, there will be negative pressure, and outside, due to the water, the presence of the pressurized water, it will see a higher pressure. And this can create difficulties in building the engine. So that's why typically we consider that 100 degrees C is a max for the heat recovery in the engine. So if I'm doing this, then what I will see is that what we obtain is 30 to 40% in terms of electrical efficiency of an internal combustion engine. The cooling system has around 30% of heat available between 80 and 90 degrees C, and the rest, which is the heat that is available in the flue gases, at around 25 degrees C, if I'm cooling the combustion gases to 120 degrees C. So it means that the overall efficiency will be of the same order of magnitude as a gas turbine. And something which is perhaps interesting that I'm showing here, the sizes are much smaller for the cogeneration engines than for the gas turbines, which are typically of higher sizes to be installed in the system. So it means that the gas turbines will be used for big plants, and cogeneration engine, internal combustion engines, will be used for smaller sizes and smaller plants. When I'm saying plants, you can also use a cogeneration engine to heat buildings, right? Rather than using a gas turbine that is typically much bigger. In EPFL, I don't know if you know, but EPFL is heated by heat pumps, and part of the electricity that is needed by the heat pump is supplied when the temperature is very low outside, is supplied by a gas turbine that you can see not far from the metro station. Okay, where we generate electricity and heat at the same time. There is another form of cogeneration, and the other form of cogeneration, which is widely used in the industry, is the integration of a steam cycle. Integrating a steam cycle means that we are going to burn some fuel in a boiler or in a gas turbine, and we are going with this heat, we are going to produce vapor, high pressure vapor. So it means that I have the hot stream, which is the hot source of the process, and then I'm going to produce vapor from the liquid state at high pressure. And then I'm going to expand this high pressure steam in a turbine to cogenerate electricity and obtain heat at a lower pressure. Obtaining heat at a lower pressure, if the pressure is such that it is above the temperature at which the process needs heat, then the heat is also useful. Okay? So it means that now I will have a system that is going to some extent, to take the heat at high temperature, take part of the exergy out via the turbine, and send it back to the process again in the heat sink. So if I want to do this, then I have to do it in accordance with the ground composite of the process, the needs of the process. So what does it mean? It means that if I'm in this situation here, I can identify that I have a heat load that is needed at high temperature here, and a heat load that is needed at low temperature here. And then I'm going to say, okay, but why not produce high pressure steam with a boiler here, extract some energy out of the system in form of mechanical power, and release the heat at a lower temperature here. By doing this, if I'm looking at the energy balance from the boiler to the process, in fact, I have extracted energy here, so it means that I need to supply Q1 plus W in the boiler here. Okay? So, what does it mean in terms of efficiency? So what I can see is that a priori, I had to supply Q1 plus Q2 with the efficiency of the boiler. Okay? Now, with this new system, I have to supply Q1 plus W plus Q2. which means that I'm producing the mechanical power at the efficiency of the boiler. 1 unit of mechanical power produced means that I have to add this in the boiler here, okay? And that's it, because this is the Q1 I had already to pay, I have already paid for it. Okay? So in this case, what I can see is that I have an efficiency of the system, which is a marginal efficiency that is near the boiler efficiency, so 90 or 85%. Okay? And this shows that it's very interesting to try to do it, because then I'm really much better than the coal power plant that has an efficiency of 40%, or a nuclear power plant that has an efficiency of 30%. Okay? Here I will have an efficiency which is near the 85 to 90% for the electricity production. So, and when I'm saying this is the additional amount of fuel per additional amount of mechanical power produced. Okay? When I'm looking at the composite curve, it's even better if I'm looking at what is happening below the pinch. Because below the pinch, I know that I have too much heat. So if, and I was asking you, give me the highest temperature at which you can take the heat out. The reason for this is that if I have heat at high temperature, I can use it to evaporate a fluid, which is perhaps not steam. It can be another refrigerant. Okay? But with this, I can co-produce mechanical power and release less heat in the environment. So in this case, I'm just going to convert the heat, the waste heat, into useful energy, work. Okay? So this is the principle of converting waste heat, and the waste heat is the heat that is below the pinch, I remind you, okay, into mechanical power. So it's a very nice and efficient system. And there is just something which we have tried to avoid. The efficiency, sorry, I'm going back here. The efficiency of the production of, so it's not here, it's here. Yeah, the efficiency or the amount of electricity that I can produce when I have a heat source at a given temperature and a cold source, cold sink, sorry, at another temperature, is given by the Carnot factor here. Okay, so the source and the sink are here, which means that the trends would be to try to increase the ratio here to its maximum value. So try to increase the temperature of the source and decrease the temperature of the sink. Okay? And the risk is that I will start to do something, sorry, like this, where I will produce high pressure steam using the boiler and expand it into a steam turbine that is doing a very big pressure difference, but releasing the heat to the environment, so to the cooling water. So a condensing turbine that heats the environment. Okay? And in this case, in fact, what I can see is that it has no influence at all on the process requirements. Okay? So it means that this system, by taking heat from above the pinch to below the pinch and producing mechanical power, is exactly like buying a normal power plant. And I can assure you that you will be less efficient than the best power plants that exist. So it means forget about it. Okay? There will be no benefit at all. So the conclusion for this is that as we had a rule for integrating heat pumps that were saying try always to use a heat pump that takes heat in the waste heat source and make it available in the heat sink, which is the principle of the integration of heat pump. For the cogeneration is the reverse. Always integrate cogeneration either all above the heat pump, so take the heat from above the heat pump, the pinch point, and extract mechanical power, but send the heat above the pinch point, or take the heat from below the pinch point, extract mechanical power, and release the heat in the environment. Okay, and never try to take the heat that is available above the pinch point to produce mechanical power and release the heat below the pinch point. Okay, this would be create a penalty, and you will not be competitive. Okay, so those are the rules for the cogeneration. And something which is important there is that the cogeneration is bounded by the heat cascade. So I can always take heat that is available somewhere in the process. It doesn't have to come from the utility. I can have exothermic reactions that are going to produce heat. Okay, I can take the heat out. Okay, but I have to send it back, and there will be a constraint. Is that this one has to be positive. Okay, otherwise the system will not be 100% feasible. So it means that cogeneration is really efficient, but it will be blocked by the energy requirement, the heat cascade of the process, and the flow has to be defined and will be blocked by the amount of heat that is available in the system. Now, if I have now to evaluate the profitability, I will have to make an analysis where I will have to look at what is the price of the fuel, what is the value of the electricity, and there will be two values of the electricity because you need electricity for the process. So if the electricity that you need is produced by your cogeneration unit, then it's perfect because you save the price of the electricity that you buy. Okay? But it might also happen that you will be in excess of electricity because your system is producing a lot of electricity compared to the amount that you need. And in this case, you will have to negotiate a reselling price, okay? A feed-in tariff. Okay? And then you will have to negotiate with the electricity distributor. And there you will most probably in competition. You have to know that the cost of electricity has always two parts. One that is the transportation of electricity, and it makes more or less half of the price. There is a small amount that is related to taxes. And then afterwards is the energy value of the electricity. Okay? But half of the price is coming from the transport of electricity. So it means that if you do not import, you will not pay for the transport of electricity and for the production of electricity in the grid. If you have to export, you will have to pay the transport. Okay? Which means that it will be less interesting. Another important element is that a boiler is easier than something which is rotating, a gas turbine, an engine, or a turbine. Okay? And this is going to, as you have things that rotate, typically you have more maintenance. You have to add lubricants, you have to take care about stability, etc., which typically requires more maintenance, so you will have also to pay for the maintenance. And of course, you will have to use this because you have to do an investment. The longer time, operating time that you can. Okay, so the operating time will also be very important. So it means that sometimes you will identify that you have a very nice opportunity for a cogeneration unit, but you will realize that it is only for 100 hours a year, and then you will forget about doing the investment. So the operating time is important, and afterwards you will have to consider the annualized investment. So at the end, you will have a cost formula which will take into account the operation and the investment being annualized. So all these things you know how to do it, and the operation will account for the electricity that you, the fuel that you consume, the net electricity that you buy, minus the electricity and the cost of the electricity that you will export times the time of operation, to which you will have to add the maintenance costs. Okay, so it means that the formula is just more explicit here, but it's exactly the same. So with something which is important is that you will have to compare this cost with the avoided cost. And the avoided cost is mainly the electricity that you do not have to buy and the fuel that you do not have to spend in the boiler because you are spending it in the cogeneration unit. Okay, and if you have this, then you will be able to define what is the best or the profit generated by the cogeneration unit. Something which is perhaps also important when you look at the cogeneration unit is to identify who you are. In a sense that sometimes there are electrical companies who are going to install a cogeneration unit on your plant. And what they will consider then is to define what is the cost of producing the heat. Because they will buy fuel, they will have the electricity, and they will sell you heat. So it's important to know at which price they have to sell you the heat and to give you some part of the benefit. So they will have to calculate at which cost, specific cost, the unit is going to is going to deliver the heat. So it means that I need to calculate the cost of the unit of heat, considering the investment of the cogeneration unit and considering the income coming from the electricity. Okay? In this case, you know how much you will have to pay for the heat that you will receive from the cogeneration unit. And of course, it depends on the thermal and the electrical efficiency of your device, of the cost of the fuel, of course, the cost of the maintenance, and then here, the time during which you will operate. That is the numerator, so the heat load and the time of operation, that is the numerator of the investment that you have to do. I can also do the same if I'm looking at the cost of electricity. So now you can then compare the cost that is proposed to you by your electricity producers with the cost that you can obtain from the cogeneration unit. So you will be in the plant, you say, okay, I'm accepting to pay the same value for the heat as I was doing before, and I'm going to calculate or attribute the additional cost that is mainly the maintenance and the investment that is done in addition to the production of electricity. So I'm paying an additional amount of fuel that I'm attributing the electricity, and I'm attributing the investment to the electricity production. And then I'm obtaining the cost of electricity. So in this case, I'm deciding to replace my boiler, accepting to pay the same price for the heat, and defining how much I will, what will be my cost of producing the electricity. And then I will compare this value with the cost that is supplied by the electricity producer from the grid, and then I will see if I have or not break even. Okay, if I'm better or not. Okay, and of course, again, it depends on the cost of electricity. It depends by the fact that I have those two terms here. It depends on the thermal efficiency of the cogeneration engine, both the cost of the thermal and the electrical efficiency, and of course also of the thermal efficiency of the boiler. Okay, and there is a third situation, is when you are at the same time you are going to make an investment for someone else. Okay, let's assume that you have one client that is the one that is going to buy the heat, and another client, which is the grid, that is going to buy your electricity. And you decide to make the investment as an intermediate to some extent. And you will have two clients, the process and the grid. In this case, it's fair to try to say, okay, what is the cost of the electricity production and what is the cost of the electricity, of the heat supply, okay? And of course, you will not say that the value of electricity is the same as the value of the heat, because you know that in this case you will not be competitive, okay? So typically what we can do is to say that the cost of electricity will, and the heat will be related to the temperature level, the heat will be related to the temperature level at which I'm going to supply the heat. So I'm going to use an expression like this, where I'm going to say that my cost of the system, which is buying the fuel and doing the investment, it is going to be distributed, is going to be used to provide one service, which is electricity, and the other one, that is the Exergy value of the heat. Okay? And from there, I will be able to define what is the cost of the Exergy. Okay? My system is providing electricity and the Exergy value of the heat, which means that I can calculate the cost of the Exergy. And then I will say that the cost of electricity is pure Exergy, and the cost of the heat is Exergy multiplied by the Carnot factor, so that I will be fair with the cost of electricity and the cost of the heat. Okay? So, in conclusion of this part, to supply heat to a process, I can either do combustion or cogeneration in different types. So gas turbine, internal combustion engine, or reduce the value of the heat using a steam cycle. Okay? This has to be combined with what we have learned before. We have learned that heat pumps can also be used in order to supply heat. Okay? And we have seen that it was important to do it across the pinch and never below or above the pinch. Okay? So it means that everything is already set for heating, where I will have competition between the different types of technologies. Okay? Yeah, I can continue with the last dimension, which is the refrigeration. Refrigeration is all what is happening below the pinch, below the ambient conditions. So it means that I have to supply heat below, to remove heat from below the ambient conditions. So it means that first I'm going to solve the cooling of the system that can be done by cooling water, for example. And then I will identify the amount that needs to be done by refrigeration. I'm going to use a refrigeration cycle. A refrigeration cycle is a heat pump. Okay? It means that it is going to take the heat from below, below the ambient conditions, and with the help of a compressor, is going to change temperature level in such a way that it reaches a temperature which is above the ambient conditions. And this will then and it will deliver the heat to the ambient. So it means that I'm going to then have, for example, a cooling water that will be used in order to cool down the refrigeration cycle and the process. Okay? Something which is important here is that I will have to remove not only the refrigeration load, but also the amount of mechanical power that is put in this compressor here. Okay? Because the energy has entered the system and has to be evacuated to the environment. Okay, so at the end, so the refrigeration is to some extent a heat pump that is not well placed. Okay, but I have no choice because I cannot cool the process at a temperature which is below the ambient conditions. Okay, right. And of course, there is more than one configuration for the refrigeration. You know that you have the simple configuration which is only with one stage. But as soon as the compression ratio increases, it might be useful to do something which is that already do intermediate flash in the expansion. So the system is going to work in this way. You will condense the liquid, produce the liquid here, expand it in a first valve. This first valve is going to go into a flash drum that is going to separate the gas and that is going to produce the liquid. The fact that we separate the gas here allows me to make this part, so the amount of gas that is here is going just to cross this compressor here, compression stage here, okay? And the second part, the liquid, is going to be expanded into a second expansion valve, which will produce a mix of liquid and gas that is going to supply the refrigeration effect here. So it will supply the whole amount that is needed here. And it will enter this compressor. So the idea of doing it in two expansion steps allows this amount of gas of not having to be compressed from below here to above here, but just being compressed for the medium stage. Now, if I'm more clever, looking at the demand that is available, that is needed here, I can do something which is a little bit more sophisticated by saying, okay, instead of having only one exchange here, what I can do, if I have a two-stage here, I can do an intermediate cooling here. So it means that I'm going to evaporate a little bit more of gas there, okay, before entering into this flash drum here, which means that I will have a higher flow here that will be only compressed by this compressor here. And I can then supply the refrigeration cycle, the refrigeration need at an intermediate level. Okay? So now I have a system which has two stages, one below here, and a second one at a higher pressure here. And as the amount that is going to do the evaporation here is only going to make this cycle here, you will spend less mechanical power and you will be more effective. And in fact, if I want to be even more clever, I can even do the following. So I still have the expansion at the lower temperature here, but what I'm going to do here is that I'm going to send back the heat here because there is a demand of heat here. So it means that I'm going to make an intermediate loop here, which is some sort of a heat pumping. Okay? But this heat pumping is only feasible if I can take this amount of heat out of the process with a higher pressure here, which is what is going to happen here. So by doing this, in fact, I'm integrating some sort of a heat pumping inside the system, and I'm still closing the balance, but I have to refrigerate, I have to compress less. So it means that at the end I will spend less mechanical power and I will be more efficient. And in this case, I will have a three-stage cooling, 1, 2, and 3, with an intermediate condensation which is happening here. In this case, the system is really optimized and is going to minimize the amount of mechanical power that will be consumed, okay, by still supplying the whole energy needs of the process. And this brings me to the to one of the difficulties that engineers will have. You will see that you have a lot of ideas. Okay, different types of cogeneration, different pressure for the steam cycle, different pressure for the Rankine cycle, different pressure levels for the refrigeration cycle, different types of refrigerant, different types of fluids for the organic Rankine cycles, the use of heat pumps in a system, okay, which means that you will need something that will help you to decide. So I'm going to make a break, unless you have questions, and I will give you a flavor of how we will solve the problem. Okay. Okay, so let's make a break of 10 minutes, and then I will give you a flavor on how we can solve the problem. Following problem, which is the creativity of engineers. Okay, and I hope you to be creative, so have more than one idea. And the reality for this is that you know when you know a list of rules that results into a list of options. Okay, so the question is, how do we then select among options? So the way to do it is by realizing that when you analyze a composite curve, you are able to identify temperature levels for Rankine cycle or heat pumps is pressure levels. Okay? And what you would like to know is if you are going to use the unit. So it's a decision, yes, no, I'm taking a heat pump or not. And if I'm using a unit, I would like to know at which level. So how much? Okay. Those units are related to hot and cold streams because they deliver heat or take heat in the systems, for which there is a heat load that is already defined for a given flow rate, which is calculated, expected flow rate, that I will multiply by the level of usage. So I would like to know how much I'm going to use of these hot streams. It might happen that I have more than one stream. Okay, for example, a heat pump has a cold stream and a hot stream. Okay, and they will be all multiplied by the same amount. Okay, so it means that if I'm increasing the amount of the evaporation, I will have to increase at the same time the amount of condensation. Okay, at the same time, I know that this unit is going to consume electricity. Okay, so, and this amount will also be multiplied by the level of usage. And I will have also to account for the balance of electricity. Okay, and if I'm using the units, I will have to buy it, so it means that I will have to pay for a given investment and I will have to pay for a given operating cost. So the way I'm going to solve the problem is by doing the following, using the following model. So on the one hand, I would like to calculate what is the minimum cost of supplying the heat and removing the heat of the system. So I'm going to write an objective function, which is minimize as a function of the level of usage and the existence of the different units. The cost, which is the operating cost, and the operating cost is how much I pay for each unit that I'm using as a function of the level of usage, plus the electricity that I have to buy, minus the value of the electricity that I'm going to export, multiplied by the operating time during which I'm going to use all those units. Plus the investment, which is related to the level of usage of the unit and the existence of the unit. So how do I define the flow? I'm going to define the flow by calculating the flow of each of the streams that I have in my system, for which I have no clue about what is the flow. So I'm going to write a constraint that is going to say that all the process streams have to be satisfied in the heat cascade. So I'm going to write for each temperature interval heat cascade equation that I'm going to close with the flow of the contributions of all the hot and the cold streams that I will have related to each of the W here, which is each of the units that I have in my utility system. So here, I do not know what is the flow of each of the units, but I have a contribution in each of the temperature interval. Okay? To this balance that is calculating the heat cascade, so it's exactly the same as before, except that there is some flows that are unknown here. I will have to add something which is an infeasibility constraint that is going to say, a feasibility constraint that is going to say that the heat that is cascaded has to be positive. Okay? So now I will calculate the flow here in such a way that the air that is here is always positive. Okay? And as I'm creative but not an idiot, I can already say that I don't want to buy magic energy, so it means that the heat coming from outside is equal to 0, and the rate heat released out of the system is equal to 0, meaning that in the list of all the utility streams that I have put in the system, I know that I have at least the one that are able to heat and cool the system. Okay? But now, as I'm aware about heat pumps, as I'm aware about cogeneration unit, I will add to the constraints of the heat balance here another constraint that is going to define the electricity consumption and the electricity production. So what I'm going to do is that I'm going to consider that for each of the units I will have a contribution of electricity that relates in fact the heat of the flow with the electricity that is produced, and that will be multiplied by the multiplication factor which is here. And I'm going to make the contributions of all the units plus the electricity that I'm buying, which will be the electricity that is needed by the process. At the same time, I will consider the export of electricity, which allows me to calculate how much I'm going to export. And of course, I cannot write two inequality constraints, which means that this one needs to be positive, while this one is an equality constraint. By doing this, I will calculate if the term export is equal to 0 or the term import is equal to 0. Okay? Now, how do I make the choice? And the choice is made by this equation here. What is this equation saying is that, so we have in fact two terms here. On the one hand, we have something which is going to say that the flow, that is binding the flow to a minimum and a maximum value here, and that is multiplied by the value, the variable here, which is an integer variable. This integer variable is saying if yes or no, I am using the unit. Yes means that the value is equal to 1, no means that the value is equal to 0. And what I can see if I'm applying this to this equation here, when the value y is equal to 1, it means the unit is selected. In this case, so I will have one here and one here, it means that the flow will be between the minimum value expected and the maximum value. Okay? So you can choose whatever you want, but it is between the min and the max. Okay? The y being equal to 1 means that the fixed cost will also be activated here, and the fixed maintenance is also activated. If now the unit, and of course, so you can see that the flow is positive, so it enters in this equation and in this one, and here as well. Okay? If now I'm not choosing the unit, so it means that the integer variable is equal to 0. Okay? So if y is equal to 0, what you can see is that here this will be 0 and this will be 0. So it means that the flow will be between 0 and 0. So the flow is equal to 0. It means that this is going to be 0, so the unit is not contributing to the electricity balance. This will be also equal to 0, so it means that it is not going to contribute to the heat cascade. And this will be 0, so it means that it will not cost in terms of operating cost. It will be 0, so no fixed maintenance. And 0 here means that it will not have a fixed contribution and a proportional contribution. So it means that the unit has disappeared from the analysis. Okay? But of course, for doing this, I need something that is going to decide what is the value of the y. So is it 0 or 1? And what is the value of the flow if the value is equal to 1? Okay? This problem is known as being a mixed integer linear programming problem. And this is the technique that will be used in order to calculate the optimal flows in your system. Something which is perhaps important is that you have to ask me, why do you use here a linear equation here? And I would tell you that I'm using a linear equation because a linear problem is much easier to solve than a nonlinear one. Okay? And it's much easier to converge. So you can ask a mathematical tool to solve a problem and it will converge. That's the interest of using a linear term. But it means also that I have to be smart in defining the values, because I know that the investment is indeed non-linear. So I have to transform this equation into a new one, which is a linear one. And what I will do is that I will linearize at a certain place. And that's what I'm going to do. I'm going to take 2 points and I'm going to calculate the slope. And the slope is going to define the C2 here. And I'm going to see where it then intersects with the zero axis to define the fixed contribution, which is the C1 that is here. And I have to be smart in the sense that I have to choose the place where I'm doing the linearization. I do not have to be to go outside of the scope, so I need to be near the typical size. But as I have read the composite curve, I know already what is the typical size of the system, so I will not do a linearization here if I know that the value is on this value here. And to be sure that I'm still significant in the calculations, I will use the min and max. So I will not allow the system to go up to here. I will say my system is valid between this level and, for example, this level. And I will stop if I'm going farther than those levels. Okay, so this is an explanation on how we are going to solve the problem, and this is how it is proposed in osmosis. Next week I will explain you how to solve the MILP problem, so I will skip all this part here because I'm going to present it next week. And I would like just to show you what is the way you are, how you will see or state the problem with the program that you are going to use. So you have seen already that you have to give values, which is the cost of the two costs of operation, the two investment here, and the min and the max. So what you will have to do, as soon as you will decide that the type of the process is utility, then the operating parameters will be introduced by the COP1, which is the fixed operating cost that is going to apply with the integer variable use of the unit. The cost of operation 2, which is the proportional cost, which is a function of the multiplication factor, which is going to multiply all the streams that you have in the system, including the power, okay? And that will enter in the power balance. You will have also the impact on the investment, so the fixed investment and the proportional investment that is going to appear in this way. And the min and the max flows that will define the range of appearance of the multiplication factor, so the FW that I have shown before, okay, which will be named mult in osmosis, okay. And just to let you know here, there is a trick, because you can also formulate the problems with different operating conditions. In your exercise you have only one operating condition, but in reality you can operate the process with several operating conditions, which means that you will have to decide if you use the unit at the given operating state or not, and you will have to buy the unit at the given buy the unit or not, which is represented here. So it means that in osmosis you will have the possibility of calculating or integrating utilities, and it will be exactly the same as all the hot and cold streams of the process that you have introduced before, except the stages, which is defined by selecting a different type. So the more you have ideas, the more sheets you will have with those units. You will have the hot and the cold streams that will be defined, and the system will calculate the multiplication factor that will always be between the Fmin and the Fmax that you define here in your configuration file. Okay. So this will be the conclusion of today. Next week I will explain a little bit more, because I want you first to explore a little bit how it works. So the conclusion of today is that with the use of the ground composites, you are able to identify the options that can be used in order to convert the energy that you buy into the useful energy for the process when the process has done the heat recovery. You can characterize the utility streams by defining the operating cost, defining the investment cost, and as you are going to linearize it, defining the minimum and the maximum bounds of the different units. And by solving a mixed integer linear programming problem, you will be able to identify what is the best set of the utility units that you can use in order to supply the heat that you need after the heat recovery at minimum cost. Okay, which is what you expect to do, and which is the expected answer that your boss is waiting from you. Okay, do you have questions? Typically there are no questions because you have not used it. So the next step is to use it. So now I let you with the assistant, and hoping that you will go fast towards the heat recovery and the composite curves, and from there proposing a list of heat pumps, proposing a list of hot and cold cogeneration units or whatever to satisfy the needs of your dairy. Okay?